Is the board visible, everyone? Is the board visible to all of you guys?
Yes.
Right. So I thought of taking more time today, but some of you said that, sir, they are going to write the test. I have asked you in the group at 2 o'clock, something like that. Only two of them responded, sir, please take the class at 2:30. Rest all, none of them have responded. So we are in a democracy, I think. So you have the authority and the right to express whatever you feel like expressing. Okay. So obviously everything will be considered from all aspects. I'll think and I'll schedule the class. Okay. So I thought 2:30 to 4:30 would be a better time. So anyhow, by the way, uh, then in the evening, some or the other work will be there. Obviously, so I got little bit occupied, guys. So 8:30 is the time I've scheduled. So maybe we can continue till 10:15 today. Okay, I'll try to give a quick recap of current electricity. If that is done, then we will solve some questions related to current electricity as well. I hope the board is visible to everyone, right? Yes, no, guys, all of you?
Yes, sir.
Right. So basically, current electricity is such a chapter where at times four questions can also be asked, at times two questions can be asked. So on an average, you can say 2 to 3 questions can be asked from this particular chapter, guys. So by Almighty's grace, we were successful enough in completing 4 chapters, out of which you will get a maximum of 8 questions. Okay, a maximum of 8 questions from the 4 chapters that we have done, right? Anyhow, you need to understand that till 21st or 22nd, because I am fasting, guys. Maybe there will be a kind of constraints for us. For other 2 weeks, you can consider. But in the next 2 weeks, from 22nd onwards or 23rd onwards, till May 5th, May 6th, to sorry, yeah, May 6th. Till then, whatever time I can spend with you people, whether it is 3 hours, 4 hours, right? I will try to spend with you people for sure. Okay, so there will be few constraints till 21st, 22nd, right? So I am ensuring that those constraints are also not there, but at times again I cannot say anything to that. So there will be certain constraints, but whenever we think that we are, you and I, we both are free, right? Then there should not be any hiccups in taking extra session, guys. Maybe 3 hour session, right? On the other day we took around almost 2 hours 45 minutes, something like that. So like that we can continue, I guess. Okay, so without further ado, let us move ahead. So basically, current electricity deals with how charge is flowing, what are the different measuring instruments, right? What would be current electricity? What is the basic definition of current? What is the total charge flown, right? Relations between drift velocity, right? And types of cell, different combination of cells, combination of resistors, RC circuit, right? Power, basically questions will come from power again. Wheatstone bridge will be there, meter bridge will be there, right? Potentiometer questions. All the potentiometer questions, not many have been asked in recent NEET exams, guys, but till AI PMT was there, lot of questions from potentiometer were also being asked. Okay, anyhow, we'll cover everything and we'll also see questions as well. So the test that was supposed to be written today, hopefully you'll be writing tomorrow, guys. Okay, so basically what is current again? It is rate of flow of electric charge, guys, right? Whenever we make use of a term rate, what is the term rate? Whenever a term rate is used, it stands for differentiation, guys. If simply rate is given, obviously it will be differentiation with respect to time. And what does differentiation give? Differentiation usually gives a slope, guys. What does it give? Differentiation will give slope. So rate of flow of charge will be called as current. By definition, current will be given as, by definition, because it is rate, it is dq divided by dt, but it will also be equal to your instantaneous electric current, guys. So instantaneous current will be dq divided by dt. Average current will be delta q by delta t. I can also write this as the total charge flown per total time taken. It is the total charge flown per total time taken. Average current can also be written as total charge flown per total time taken again. Right, instantaneous current will be anyhow dq by dt. By definition of current, current will be written as dq divided by dt. This is by definition. It also happens to be instantaneous current, guys. And what is dq by dt? It is going to give a slope of charge versus time graph. So if charge versus time graph is given, slope of charge versus time graph is going to give us what, beta? current. Okay, in the same manner, if you can just take it something like this, so dq value, what we can write, I can write it as dt. D basically stands for differentiation, guys. If I want to remove differentiation, I'm going to apply integration. So I'll get it as integral I dt, let us say from some t initial to some t final, from some q initial to some q final. So if I just solve this, you will get integral of dq, integral will be q only, which will be integral of I of t dt, guys. I dt or I of t dt you can write. So what are we going to get here? On the left hand side, we are going to get the total charge flown beta. What are we going to get? We are going to get the total charge. Delta Q you can say, which is Q final minus Q initial, which is also happening to be total charge. So how are we going to obtain total charge beta? Suppose from differentiation, we will obtain slope. Whereas from integration, what are we going to obtain? From integration, we are going to obtain area, guys. So this is area covered under which graph? Current versus time graph. So this is your area covered under current versus time graph. With which axis again? Current versus time graph with time axis only. So two things we can understand again from here, right? If charge versus time graph is given, slope of charge versus time graph will give us current, or to be precise, slope at a particular point will give us instantaneous current. Slope between 2 points will give us average current. Clear? And always remember, current does not obeys, it may have a direction, guys, right? It may have a particular direction, it flows opposite to the direction of flow of electrons. It may have a particular direction, but it does not obey vector addition, laws of vector addition, guys. So that is the reason it is a scalar quantity. Electric current, although it may have magnitude and direction, it will not obey laws of vector addition. That is the reason it is which quantity, beta? Scalar quantity. It also happens to be the fundamental quantity. So dimensions of current can be written as A, guys. Clear, all of you? Basic thing. Again, what we can also calculate, how to calculate total charge flown. If current versus time graph is given, again, this will be useful in AC also, guys. If current versus time graph is given, the area covered under current versus time graph will give us total charge flown. You also have one more term called as current density. So by definition, it is current flowing per unit area, guys. By definition, what is it? It is current flowing per unit area. Now, current is a scalar quantity, but current density will be a vector quantity. As you can see, current density is a vector quantity, guys. So if you have uniform current density, right? Whenever you have uniform current density, I will write current as J bar dot A bar. Whenever we have uniform current density, J bar is called as your current density. It is current flowing per unit area. Whenever you have uniform current density, current will be represented as J bar dot A bar. Whenever you have non-uniform current density, guys, I am going to make use of integration, right? Integral J bar dot dA bar. This is very important again, right? And we can also write current density in terms of drift velocity. See, what is the reason for flow of current? Basic logic. The reason for flow of current is potential difference, guys. Current always flows from higher potential to lower potential. And we also know current will flow opposite to the direction of flow of electrons. So current is flowing from higher potential to lower potential. Current flows opposite to the direction of flow of electrons. So can I say electrons will flow from lower potential to higher potential or not, guys? Right? So electrons will be drifting. Because of the drift of electrons in conductors, we have current flow, guys. Okay, so what is drift velocity in general? It is the average velocity with which the electrons will drift from low potential end to high potential end. So I can also write current density in terms of average density, sorry, in terms of drift velocity. So J bar can be written as NQVD bar, or if you want, you can write J bar as NEVD bar as well, guys. VD bar is the drift velocity of electrons, which is the average velocity with which the electrons will be moving from lower potential end to higher potential end, guys. Right? So these are the current and current density. Current density is important. Again, direct question also you may get, guys. Just dot product, you may get a question. So whenever current density, uniform current density, constant current density is given, I can write current as J bar dot A bar. However, if you have non-uniform current density, I'm going to make use of integration again. We can also represent current density in terms of drift velocity. What is drift velocity? I have told you, guys. Right? So it is the average velocity with which free electrons will drift from low potential end to high potential end. Now, what in general is drift velocity? See, again we have something called as Ohm's law. We will study in general, guys. There is microscopic form of Ohm's law. So J bar will be given as sigma into E bar, guys. So E bar is the electric field. So current density is in the direction of electric field. And electric field, you know, it will always be in which direction, beta? Is it going to be in the decreasing potential direction or not? So electric field will be moving from high potential to low potential. So drift velocity, can I say this is going to be from higher potential to lower potential? Yes or no? Electric field lines will always be directed from higher potential to lower potential. But how will free electrons drift? They are going to drift from lower potential to higher potential. Yes or no? So what are we going to get from this situation? We are going to get drift velocity opposite to the direction of electric field. Clear? So I can write drift velocity as E tau divided by mass of electron into applied electric field, you can consider. I can also write, because we know current is written as J into J bar dot A bar, guys. So I can write current value as, because we know it is J into A, I can also write it as NEAVD. Okay, this is also very important. Current can be written as NEAVD. Current density can be written as NEVD, or to be precise, it is written as NE minus VD bar, guys. Okay, is that clear? So better you write here NE minus VD bar. They have given VD bar, but that is wrong again. So it is NE minus VD bar, guys. Clear, all of you? Yes or no?
Yes, sir.
So drift velocity can be given as E tau divided by m into E bar. Always remember, drift velocity will be opposite to the direction of flow of opposite to the direction of applied electric field. Okay. Now, two things are very, very important, guys. How is drift speed varying or drift velocity varying, guys? If I have same current, so I can write drift speed as, how can I write from this equation? Can I write it as Ni divided by NEA or not? N is number density. It is number of electrons per unit volume, guys. Capital N by V we can write. Suppose if I have constant value of I, right here you can see, if you have same strength of current, for same strength of current, always remember drift speed will be inversely proportional to area. Very, very important, guys. You got a question based on this in previous year. For same current, VD will be inversely proportional to area, guys. Right now, I want to write in terms of potential difference. So we know basically if I multiply and divide by resistance, I'll get V divided by NERA. Now you know resistance can be written as rho L by A. Yes or no? So as you can write it as rho L by A, we can write it as V divided by rho L by A. No, so NE rho L also you can write better. This is your drift speed in terms of potential difference. So as you can see, if potential difference is same, drift speed will be inversely proportional to the, for same potential difference, it will be inversely proportional to the length. These two are very, very important points again. I don't know, but from morning my throat is paining a lot. So these two are very important points in drift velocity again. If I have same current, drift speed inversely proportional to area. If I have same potential difference, drift speed will be inversely proportional to length, guys. There is also a term called as mobility again, right? The ratio of drift speed to applied electric field will be called as mobility, guys. The ratio of drift speed to applied electric field will be called as mobility. So I can write that mobility as Vd by E. So from here, Vd by E will become E tau by M, guys. Tau is called as relaxation time. Relaxation time means the time for which the electrons can drift freely without any collisions. Okay, so that is your relaxation time. So here we can consider mobility value will be given as Vd by E, which is E tau divided by M. Please remember, the mobility, it may be expressed as Vd by E, just like capacitance is expressed by charge by potential difference. It is neither depending on charge nor on potential difference. In the same manner, mobility also, guys, it will be independent of the drift speed and electric field. It will be independent of drift speed and applied electric field. Clear, all of you? Current is dq by dt. Charge will be integral I dt. If you have uniform current density, current can be written as J bar dot A bar. If you have non-uniform current density, I can write current as integral J bar dot dA bar, right? Current density can be written as NEVD. Current can be written as NEAVD. So drift speed can be I divided by NE capital A, or we can write V divided by NE rho L. So for same current, drift speed inversely proportional to area. For same potential difference, drift speed will be inversely proportional to length. Is that clear? So we have two forms of Ohm's law, guys. One is microscopic form, other is macroscopic form. Microscopic form, I have told you, right? Whatever is current density, it will always be in the direction of applied electric field, guys. J bar is sigma into E bar will be called as your current density. Sigma is your conductivity, guys. Opposite of resistivity, you can write. In the same manner, macroscopic form of Ohm's law, if I consider, V will be directly proportional to I, we are going to write. So I can be written as V divided by R. Now, please don't say V is potential here, guys. V is not potential. V is potential difference again. What is V? V is potential difference. So whenever we talk about ohmic conductors, what are ohmic conductors? Those conductors which are going to obey Ohm's law again, right? Macroscopic form of Ohm's law. So for ohmic conductors, IV curve is a straight line. For which type of conductors? For ohmic conductors, which obeys Ohm's law. For non-ohmic conductors, IV curve will not be a straight line, it will be a curve, guys, right? And always remember, for small potential differences, small current only, V will be directly proportional to I. I can write V as I into R. Clear? Two forms of Ohm's law, microscopic form and macroscopic form. Microscopic is J bar is sigma E bar. Macroscopic will be V is equal to IR. So for ohmic devices, IV curve or VI curve will be a straight line. For non-ohmic devices or non-ohmic conductors, it will not be a straight line, it will be a curve, guys. Now, color code of resistors is very, very important, right? 2018, 2019, consecutively, they have asked color codes, guys. I'm not sure, I think 2020 also it was asked. So basic logic we are going to use in color coding again, right? So you will be given something like this. This will be first digit, second digit, multiplier, and tolerance, guys. So what is the basic logic to remember? BB Roy, what I say is BB Roy went to Great Britain, right? Instead of with, usually comes with W, guys. With usually comes with W, but I'll take SMS again. We'll use with. Okay. So with his gray wife, guys. Okay, to buy gold, silver, and no color you can consider. So BB Roy went to nothing, guys. So BB Roy went to Great Britain with his gray wife to buy gold, silver, and no color. So this is the basic logic that you will remember. BB Roy went to Great Britain to buy with his gray wife to buy gold, silver, and no color, guys. So you can remember. So suppose if I say, let us imagine, right? Let us say this is red color. Okay, let us say this is the first color is red. The second color, let us consider, is gray, guys. Okay, the third color, let us consider, is yellow. And fourth one is made up of silver, let us say. Now, how do you write the resistance for this? So red, what is corresponding digit for red? You see 2. So I'll write 2 here first. Then what is it followed by gray? So I'll write 28, guys. This is first digit, second digit. Then I should get multiplier into, what is the multiplier for yellow? You can see it is 10 power 4 into 10 power 4 ohm. Then we will write tolerance plus or minus. For silver, what is the tolerance? You can see 10%. Okay, so this will be the resistance of the wire, guys. BB Roy went to nothing again. We'll simply use went to again. BB Roy went to Great Britain with his grey wife to buy gold, silver, no color. I hope you understood. Again, it's very important. Color code of resistors. Definitely questions can come from this again. Understood, everyone? Yes or no?
Yes,
Let
sir.
us. So electrical resistance and resistivity. Let us focus on that. So as we know, for ohmic conductors, V is directly proportional to I. If you remove proportionality sign, we are going to get a proportionality constant. So what is R here, guys? R happens to be resistance, but it is a proportionality constant. What is it? It is a proportionality constant. So in general, you cannot say that it will depend on V or it will depend on I, guys. Right? For a material, its resistance will remain constant, its resistivity will also remain constant. So as you can see, resistance can be given as rho L by A into or M divided by N E square tau A. So from this, if I just compare both of them, guys, what are we going to get resistivity as? Resistivity, we can write it as, it's already written here. The resistivity can be written as M divided by N E square tau. M is mass of electron, N is number density. Number density can be written as number of free electrons per unit volume. E is the basic unit of charge, guys. Tau, as I said, it is relaxation time, the time for which electron can move freely without any collision. Is that clear? So resistance can directly be written as rho L by A or Me into L divided by Ne square tau into A. So resistivity can be Me divided by Ne square tau, guys. And always remember, resistivity, if I consider, resistivity is simply property of material, guys. What it is property of material. What does it not depend on? It does not depend on the dimensions of conductor. It simply depends on nature and temperature of the conductor. It means if temperature is changing, resistivity is also going to change. Now, let us take a hollow cylinder again. They're asking us to find resistance, guys. So what we are taking, they're asking us to find resistance between these two ends. They're asking us to find resistance between these two ends, guys. Okay, so what is the length here? L happens to be the length you can consider. Resistivity is already given. So we know we should take it as rho L divided by A. So how to take this area of cross section? So what is the area of cross section? Only this part is area of cross section, guys. So it is in the form of what we can consider concentric circle you can consider. It is annulus of a disk, we call it as. So what will this area be? It will be area of larger circle minus area of smaller circle. So that is the reason we write this as rho L divided by pi r2 square minus pi r1 square. You may get such type of questions also, but again, they're not going to be asked. In general, you should be very careful how to take area of cross section, right? From whichever end current starts to flow, whatever is the area of cross section of that end, that should be considered as area of cross section while calculating the resistance. Please do remember, it is given as V by I. So generally, resistance will be given as V by I, or it is given as rho L divided by A, or it is written as Me into L divided by Ne square tau into A beta, where this particular quantity Me divided by Ne square tau happens to be resistivity of the material. Resistivity will depend on nature and temperature. Okay, these two things only will affect the resistivity of the material, guys. Let us see how is the temperature difference again. As I said, resistivity will change with temperature. So for different materials, as temperature increases, resistivity will change. Its corresponding resistance will also going to change, guys. So as you can see, for conductors, usually what will happen? As temperature increases, for conductors, usually, as temperature increases, resistivity will increase. So if resistivity is increasing, obviously resistance will also increase, guys. So basically, alpha value is coefficient of resistivity again, right? Just like we have coefficient of thermal expansion in thermal properties, which we'll deal later in the second half of this particular course, right? Alpha will be called as temperature coefficient of resistivity, guys, right? And that usually will be very small, guys. So we will consider linear variations. Yes.
Sir, how is charge density proportional to the drift velocity?
How is?
Charge density varies with drift velocity.
There is a relation for that. It is directly proportional to drift velocity. Just now we have seen, no? It will be in opposite direction.
It will be in opposite direction.
Charge current density as well as your drift velocity will be in opposite direction, directly proportional to each other but in opposite direction.
Okay.
Temperature dependence of resistivity, guys. So as temperature increases, resistivity will increase. In the same manner, resistance will also increase. Now alpha value basically is very small value, guys. Alpha is basically very small value, so we usually consider the resistivity changes to be linear changes, means they are going to follow a straight line. So what we can write, resistance at any temperature can be written as R naught into 1 plus alpha t, guys, or alpha delta theta we can consider. So what is R naught here? R naught is the resistance at temperature 0 Kelvin, guys. It is resistance at 0 Kelvin you can consider. Okay. So resistance at any temperature, theta will be equal to R naught into 1 plus alpha theta you can write, or 1 plus alpha delta theta also you can write. So if you know resistances at two different temperatures, as you can see here, if you know resistances at two different temperatures, you will be able to calculate the value of alpha, right? Coefficient of resistivity, temperature coefficient of resistivity. You can also calculate R naught value, guys. So maybe initial resistance may be given, R1, R2 values may be given, temperatures will be given. They will ask you to find alpha, or alpha value will be given, two different temperatures will be given, their corresponding resistances will be given, and they'll ask you to calculate the initial resistance. So this formula majorly you are going to use, guys. R will be R naught into 1 plus alpha delta theta. To be precise, it is R naught into 1 plus alpha delta theta, guys. In the same manner, resistivity also, it will be rho naught into 1 plus alpha delta theta. Because rho naught we take resistivity at 0 Kelvin, instead of writing delta theta, we directly write it as T or theta, guys. Okay. T here stands for temperature. I am using theta. Theta is also temperature only, guys. So please remember this formula. It is important again. For semiconductors, how will resistivity change? Basically, for semiconductors, as you can see here, resistivity decreases exponentially. So as temperature increases, resistivity of semiconductors will decrease. We will study about semiconductors in detail in semiconductors chapter, guys. So if resistivity is decreasing, so what is resistivity, beta? It is reciprocal of conductivity. So if resistivity is decreasing, what will happen to conductivity? It will increase. How will it will increase? Exponentially increases again. How will it increase, beta? It will increase exponentially. So rho is resistivity for semiconductors. Resistivity exponentially decreases with increase in temperature. Conductivity exponentially increases with increase in temperature. For conductors, usually as temperature increases, resistivity will also increase. You got one question based on this again, guys. Okay. For insulators, because resistance of insulators will be very much high, guys, there will not be, does not very appreciably you can say, or not much appreciable change with temperature. Clear? Yes or no? So this is also an important point, but not that much necessary to discuss again. Suppose if you take two resistors and they have some temperature coefficients. So if those two resistors are connected in series, they will ask you to find equivalent temperature coefficient, guys. So in series, you will get equivalent temperature coefficient as R1 alpha 1 plus R2 alpha 2 divided by R1 plus R2. That will be the value in series. However, in parallel, you will get R1 alpha 2 plus R2 alpha 1 divided by R1 plus R2. Please remember these formulas again, right? For series, if two resistors have some temperature coefficients, right? If they are connected in series, their effective thermal coefficient will be R1 alpha 1 plus R2 alpha 2 divided by R1 plus R2. Whereas if they are connected in parallel, it will be R1 alpha 2 plus R2 alpha 1 divided by R1 plus R2. So we have insulators, we have conductors and semiconductors. For conductors, resistivity increases with temperature. For insulators, not much appreciable change because already resistivity will be high for insulators. For semiconductors, resistivity will exponentially decrease. You also have something called as superconductors, guys, right? Usually it is superconductor is a phenomena wherein which resistance of a conductor will become zero at very low temperatures. Now, what do I mean by very low temperatures? Almost 0 Kelvin, guys, right? So whenever resistance of a conductor becomes zero, that will become superconductor, guys. And basically, please remember, superconductors are going to show perfect diamagnetism. Okay, so this will also be called as Meissner effect, which is used in magnetic levitation, right? Usually metro trains you can consider, guys. So that you can consider, it will be Meissner effect. Okay, the variation of resistivity will be something like this, guys. Okay, So not necessary, superconductors are not that much essential for us. Please remember insulators, conductors, as well as semiconductors. Now, as we come to very important part of resistance again, we know resistance is given as rho L by A, right? Now, please remember, if wire is cut, what is the meaning of wire is cut? Wire is cut means area of cross section remains same, guys. So whenever area of cross section remains same, resistance will be directly proportional to length, guys. Second case, when wire is stretched, what is the meaning of wire is stretched? Volume will remain same, guys. Whenever wire is stretched, volume remains same. So I can use resistance will be directly proportional to L square, right? And you can also write, if volume is remaining same, you can also write, in addition to this, you can also write resistance will be inversely proportional to area square also, guys. Okay. If wire is cut, resistance directly proportional to length. If wire is stretched, resistance directly proportional to L square or inversely proportional to A square, guys. Clear, all of you? These 2 points are important again, rest of them not that much necessary again. So what is situation here? If length is kept constant, so we have seen area is kept constant, we have seen volume is kept constant. If length is kept constant, then resistance will be inversely proportional to area of cross section or inversely proportional to R square, guys. Clear, all of you? Yes or no? So area of cross
Yes, sir.
section, basically, you know, it is proportional to R square. So you can write it will be inversely proportional to R power 4. Area constant, directly proportional to length. Volume constant, directly proportional to length square or inversely proportional to A square. Length constant, inversely proportional to A. These three things you should be aware in case of your variation of resistances with length, with area, with volume. So these things you should remember, guys. Clear, all of you? Yes or no? So series
Yes.
grouping, as you all know, in series grouping, what is series grouping, guys? Please don't say that only current has to remain same, guys. If same current is flowing through resistors, it need not necessarily be series grouping, right? For series grouping, one of the point is there should be equal current. But very important point is there should be end-to-end connect, guys. See, end of R1 is connected to one end of R2. End of R2 is connected to another end of R3. Current is constant is one such condition. Okay, but what is important condition again? Even when in two resistors current is same, will they be in series? Not necessary, guys. They will only be in series if they have a end-to-end connect. And if they have end-to-end connect, definitely current flowing through the resistors will be same, guys. Then we have parallel combination. In parallel combination, basically, how we will identify parallel combination? If the resistors are connected between two same points, right? You take n number of resistors. If they are connected between, if you take n number of resistors, if they are connected between two same points, then such combination will be a parallel combination, guys. When will it be series combination? Important point, there should be end-to-end connect. Then only it is series. Later, current will be constant. When will it be parallel? If they are connected between two same points, then only it is parallel. Later, potential difference should be constant, guys. Is that clear, all of you? Series means end-to-end connect definitely should be there. Parallel means the resistor should be connected between two same points, right? So in case of series combination, as you all know, the effective resistance will be given as sum of individual resistances, guys. R1 plus R2 plus R3 plus so on. Whereas in parallel combination, guys, right, you will get 1 by R effective value will be 1 by R1 plus 1 by R2 plus 1 by R3 plus so on. So two things you remember: current constant in series and potential difference constant in parallel. Now, based on this, we have some important cases, guys. So let us discuss those cases as well. Now, as you can see to the right, do we have end-to-end connect? Yes. And is same current flowing? Yes. So which combination it will be? It will be a series combination. So in series combination, same current, but potential difference will be different, guys. So how will potential difference get divided? It is going to get divided in the ratio of their resistances, guys. So please remember, it will be V into R1 divided by R1 plus R2, V into R2 divided by R1 plus R1. E and V both are similar again. Okay. If your internal resistance is 0, terminal voltage will be nothing but EMF. We'll study about that in some time, guys. So current in series, current flowing through the resistor same, potential difference is not same. So how will potential difference get divided? In the ratio of their resistances, guys. Now you see here this combination. R1 is connected between these 2 points. R2 is also connected between 2 same points, guys. Right? So between these 2 points, what is potential difference? E. So in parallel, whenever 2 resistors are connected between 2 same points, which combination it will be? Parallel combination. So in parallel combination, what will be same? Potential difference. If potential difference is same, current will get divided or not, guys? So how will current get divided? It's not written here. So how will current get divided, beta? You can write in this situation, current will get divided in the inverse ratio of the resistances, beta. How will it get divided? In the inverse ratio of resistances. Clear, all of you? In series combination, potential difference will get divided in the ratio of the resistances. In parallel combination, current will get divided in the inverse ratio of their resistances. Is that clear, all of you? Yes or no?
Yes, sir.
Right. So the next one is a case with internal resistance. Here there was no internal resistance, guys. The next one is the case with internal resistance. So you can find out the total current I1, I2 and all. Okay. So I'm not dealing with internal resistance. First two were without internal resistance. The third combination is with internal resistance. So basically you need to find effective resistance here. So we got to know, as we can see here, R1 and R2 are connected between 2 same points. So it will be which combination, beta? Parallel combination. So here what will I get? Between these two, I will get R1, R2 divided by R1 plus R2. So these two I can replace with one resistor. Then as current flows, you will also have some internal resistance, guys. So plus R you can write. So this will be our R effective. And I value can be written as E divided by R effective. So when you know the total current, again I think you can find out I1 value. What is I1 value now? It will be I into R2 beta. Inverse ratio of resistances, no? I into R2 divided by R1 plus R2. Similarly, what will I2 value be? I into R1 divided by R1 plus R2. So if internal resistance is non-zero, then you need to find the effective resistance of the circuit. Current will be total potential difference divided by total effective resistance, guys. And in parallel combination, we know current will get divided in the inverse ratio of their resistivities, guys. Clear, all of you? Yes or no? The same logic has been given here, right? So now also look at this case. It is also very important case. Directly we can find, guys. The sixth case, guys. Rest all these anyhow you can understand easily. If I look at this case, guys, see R1 is connected between these 2 points. R2 is also connected between 2 same points. See, is there any element between these 2 points? No. So this point and this point are same, guys. Is there any element between these 2 points? No. So these 2 points are same again. So what is potential difference across this resistor? It will be V, or you can write it as E minus IR. We'll study in case of your cell, guys. We'll study in some time. So across this potential difference is V. Across this also, they are in parallel combination, so potential difference will remain same. So directly I can calculate currents, guys. If R1 and R2 are given, potential difference is given, current will be, so as you can see, I value is V by R1, I2 value will be V by R2. If they ask you to find total current, what will you write, beta? You'll apply Kirchhoff's junction law. Sum of currents flowing into the junction should be equal to sum of currents flowing out of the junction. Clear, all of you? Yes or no? Series combination, definitely end-to-end connect. Parallel combination, right? 2 resistors should be connected between 2 same points. Series combination, current will remain constant, potential difference will get divided in the ratio of the resistances. Parallel combination, potential difference is constant, current will get divided in the inverse ratio of the resistances. Understood? Yes or no?
Sir, will we not consider small r over here in the I1 I2 equation?
Where?
So in I1 I2, when we are writing the
Oh, no, you will not. When you know the potential difference, there is no necessity of writing a small r value.
so not over here, so in the previous one.
In the previous case also it is not required because you found out already total current, no? You already found out total current. So that only will get divided in the inverse ratio.
Okay, sir.
Okay. I have written I, no? I will again depend on R effective. R effective is again depending on small r. So definitely I1 and I2 will also depend on small r. See, very simple logic. I1 is depending on I is depending on R effective. R effective again, you see, it is depending on small r, which is internal resistance. Clear?
Yes, sir. Clear.
Now, we need to know some basic terminology in cell, guys. Three basic terminologies we'll have: EMF, internal resistance, and terminal voltage, which is also called as potential difference, guys. Okay, so what is EMF? If there is no current being drawn from the cell, no current is being drawn from the cell, whatever is the potential difference across the terminals, that will be called as EMF. When current is being supplied by the cell or when current is given to the cell, whatever is the potential difference across the terminals will be called as terminal voltage, or we call it as terminal potential difference, which is given by V, guys. And what is internal resistance? If let us say current is flowing through the cell, whatever resistance is offered to the flow of current inside the cell will be called as internal resistance, guys. Clear? All these are not that much necessary for us, but in general, just for a glance, guys. The cell, to different types of cells you have, right? In chemistry, you study that in electrochemistry. So I'm not going in detail about that. So resistance, internal resistance will usually depend on the distance between the electrodes, the area of the electrodes, and concentration of the electrolyte, guys. Whatever electrolytic solution they are taking, it will depend on the concentration as well as temperature again. Okay, although these 4 points are not required, please remember, if there is cell, no current is being drawn from the cell, whatever is the potential difference across the ends of the cell, that will be called as EMF. If current is being drawn from the cell, potential difference across the terminals will be called as terminal voltage or terminal potential difference. And whenever current is flowing through the cell, whatever is the resistance offered to the flow of current inside the cell will be called as internal resistance. Okay, now let us try to find out what will be the terminal voltage in different cases. So if I take this particular case, this is depending on, again, we have two Kirchhoff's laws, guys. One is Kirchhoff's junction law, which is depending on conservation of charge. Then we also have Kirchhoff's loop law, guys, or voltage law, we say, which is depending on conservation of energy. Okay, right. So let us try to apply. So here, if you see, let us try to apply KVL again, right? So two things are there, as you can see. EMF value, E is the EMF, V is the potential difference, we already know. So clear, when cell is supplying current, potential difference will be less than EMF, guys. When cell supplies current, okay. In the same manner, you can see in first case, cell is supplying current, guys. From positive terminal, cell is supplying current. In second case, you are charging the cell. This is case of discharging. Here you are charging the cell. When current is supplied to the cell, then in this case, when current is supplied, cell supplies current, V value will be less than E. Okay. When current is supplied to the cell, if current is supplied to the cell, then in that case, we can write V value will be greater than E. If no current is flowing, guys, if no current flows, then I can say V value will be equal to E. So three things are applicable, guys. Three things are valid. V value, potential difference can be less than EMF. Potential difference can be greater than EMF. Potential difference will also be equal to EMF. So they may give this concept again. So while discharging, you can consider potential difference is less than EMF. While charging, potential difference will be greater than EMF. If no current is flowing, potential difference will be equal to EMF, guys. Clear, all of you? Yes or no?
Yes, sir.
Let us see how to apply KVL, guys. Okay, I'll just take from here, I'll start. In the entire circuit, we have seen that there is some current flowing, guys. Okay, let us move in clockwise sense. Let us, again, all the questions depend on KVL application only. We are starting from here. This terminal is negative terminal or lower potential. this terminal is positive terminal or higher potential. So I'm moving in clockwise sense, please be very careful. So as you move from lower potential to higher potential, what will happen? Potential is increasing or decreasing? As you move from here to here, from lower to higher potential, what is happening to potential? Increasing or decreasing?
Decreasing.
अरे डिक्रीज कहाँ से हो रहा है भाई? As you move from lower potential to higher potential, is it increasing or decreasing? Increasing. So whenever there is potential increase, I will use plus, guys. Okay, so what I'll write? I'll write plus E here. Now current always flows in the direction of decreasing potential, I have told you. Yes or no? So current is flowing in this manner. So when current flows across the resistor, current flows in the direction of decreasing potential. So as you move across the resistor, what is happening to potential? Decreasing. Decreasing means I will use minus, guys. And potential difference across resistor, you know, it is minus IR. Yes or no? In the same manner, again the same current is flowing through the resistor. So we are moving in the direction of current, guys. So as we move in the direction of current across the resistor, current always flows in the direction of decreasing potential. So current potential will decrease again. So I'll write minus IR will be equal to, because you are coming back to the same point, there will not be any potential difference, beta. So I'll write E value will be I capital R plus I small r. From this I can write I value as E divided by capital R plus small r, beta. So whenever you move from negative terminal to positive terminal, plus E or plus V. Okay. Whenever you move from positive to negative, if you move from positive to negative, potential is dropping, guys. So whenever potential drop is there, you will take minus E. If you are moving in the direction of current across the resistor, minus IR. But if you move opposite to the direction of current across the resistor, plus IR, guys. So if they ask you what is terminal voltage, if they ask you, guys. So this is the cell overall. They'll ask you what is terminal voltage. Let us see, this is the cell A and B. EMF, you know, it is E and internal resistance is R. What is terminal voltage? They're asking. This is I value, as you all know. So let us say now I am moving from A to B, guys. So what will I write? I'm starting at A, so I'll write VA. I am moving from higher potential to lower potential. So what I'll write, beta? Potential is decreasing now, I'll write minus I. You are moving opposite to direction of current. Current will move in the direction of decreasing potential. If you are moving opposite to the direction of current, potential should increase. So I'll write plus IR. I'm going to reach point B, so I'll write potential at B. What we can write, beta? VA minus VB. I can write it as E minus IR. What is this? This is potential difference across the terminals, which I will write it as terminal voltage, which is written as E minus IR. KVL, very, very important, guys. Negative terminal to positive terminal, plus E. Positive terminal to negative terminal, minus E. In the direction of current across resistor, minus IR. Opposite direction of current across resistor, plus IR. Clear? Terminal voltage can either be less than EMF, greater than EMF, or equal to EMF. Three different cases I have told you. Clear? Yes or no?
Yes, sir.
Right. Let us talk about grouping of cells again. So we have different types of grouping again: series, parallel, and mixed grouping. What is the meaning of series grouping? As you can see here, guys, negative terminal of one cell connected to positive, negative connected to positive, negative connected to positive. Like that, if we continue, such type of grouping will be called as your series grouping, guys. Again, series means end-to-end connect should be there definitely. So all these resistors will be in series. So what will be effective resistance? Sum of individual resistances. And all these cells also will be in series only, guys. If you apply KVL, again you will get E1 plus E2 plus E3 plus so on. So what is the total current now? If I replace this with one particular circuit, I'll get something like this, beta. I'll get E effective and R effective. This is your capital R value. This is E effective. This is R effective. So what will be R effective? It will be sum of individual resistances. And what is E effective? It is sum of individual EMFs, guys. If you take n identical cells, for n identical cells means they are going to have same EMF, same internal resistance, guys. So if you add E like that, n cells you have. So if you take identical cells, effective EMF will become n into E. If you take identical cells, effective internal resistance will also become n into small r. Okay, so again, as you apply KVL, if you apply KVL, guys, now you see to the flow of current. What is the resistance offered by the circuit? To the flow of current, resistance offered is R as well as R effective. How will I write I value as? You will write it as E effective divided by capital R plus RF. Whether it is series combination or parallel combination, I value will be written as E effective divided by external resistance plus effective internal resistance, guys. Clear all of you? Now as you can see, if identical cells are given, right, what is effective EMF? NE. What is effective internal resistance? NR. So what will the answer be? You can see directly NE divided by N small r plus capital R. Now, if this value is very much greater, if NR value is very much greater, I can directly write I value as E by R. If the effective internal resistance is greater. If load resistance is greater, I'll write NE divided by capital R, guys. Two are very, very important again. If effective internal resistance is greater, E by small r. If load resistance is greater, then I'll write NE divided by capital R. Clear all of you? Series grouping of cells, effective EMF will be sum of individual EMFs. Effective internal resistance will also be sum of individual resistances, guys. If they are identical, effective EMF NE, effective internal resistance NR. Now, as you can see in this combination, negative terminal of a cell is connected to positive, negative again connected to positive, negative again connected to positive, negative again connected to positive. Such type is series combination, and that will be a symmetrical combination, guys. However, if negative is connected to negative, it means we are reversing the polarity, guys. So suppose if you have n cells and you are reversing the polarity of m cells, 5 cells you have, let us say 5 identical cells, guys. 5 identical cells connected in symmetry. What is effective EMF? Phi E. But out of 5 cells, if you are reversing the polarity of one cell, then in that case, you will apply this formula, guys. The equivalent EMF will be given as, or the effective EMF will be given as n minus 2m divided by E. So if m cells polarity is reversed, effective EMF will be n minus 2m by E. However, the effective resistance value is not going to change, beta. It will still be n into R only. Effective resistance will not change. Effective EMF, instead of becoming n into E, it will now become n minus 2m into E. Out of n cells, if m cells polarity is reversed, effective EMF will be n minus 2m into E. Clear all of you? In the same manner, just like parallel combination of resistors, if resistors are connected between two same points, here cells should be connected between two same points. So as you can see, guys, this is one cell, another cell, another cell, another cell, like that all are connected between two same points only or not. So such type of combination will be parallel combination, and as you can see, all higher potentials are on one side only, guys. All higher potentials are on one side only. Then please remember this formula. Effective EMF will be E1 by R1 plus E2 by R2 plus so on divided by 1 by R1 plus 1 by R2 plus 1 by R3. All these internal resistance will be in parallel, guys. So I'll get 1 by R effective will be 1 by R1 plus 1 by R2 plus 1 by R3 plus 1 by R4 plus so on, guys. These two you should remember. So if all cells are identical, so across this you will have EMF, EMF, EMF. All these are in parallel, no? So whenever identical cells are taken, guys, what will be effective EMF? I'm writing here. If identical cells are taken, you will get E only. Identical internal resistance will be R by N beta. Okay, please remember this. This is when identical cells are connected. Okay, so as you can see here also, E and R by N. So what is current flowing? I have told you it is effective EMF divided by effective internal resistance plus capital R. So as simple as that. What is effective EMF? E. Effective internal resistance R by N plus capital R. So this is also very, very crucial case again. Although it is not necessary to remember the formulas, guys, you can then by in current electricity chapter, no, you can solve the questions there by itself. There only you can apply KVL, you will get the answer. Now, in this again, if R by N value is greater, If R by N is very much greater, I'll get the EMF as current as NE divided by small r. If again, if capital R value is greater, then I'll directly get it as E divided by R. Okay, these you should remember again. Not necessary to remember, to be precise. Okay. Series combination sigma E or sigma EI. R effective will be sigma Ri. Identical cells means series combination N into E, effective internal resistance N into small r. In parallel combination, formula is very important, guys. Suppose if I say one very important case, here all positive terminals are one side. So I took plus. Let us say if polarity of E2 is reversed, guys. E2 is reversed or E3 is reversed, let us say. If polarity of E2 is reversed, then what will I write effective EMF as? Very careful, guys. E1 by R1. Here you have opposite polarity. So I'll write minus E2 by R2. Again, same thing, plus E3 by R3. So whichever cell is reversed, there you should write minus. However, in internal distances, you will just go on adding, guys. 1 by R1 plus 1 by R2 plus 1 by R3 plus so on. This is also a very important point again. Whichever terminal is reversed, right? Whichever cell terminals are reversed in parallel combination, before that cell, you should write minus sign, guys. Clear, everyone? Yes or no? I hope
Yes,
it is
sir.
clear, right? Then we have mixed grouping. Now, what is the meaning of mixed grouping, guys? You see, it is just combination of series and parallel grouping. So I'll just show you the circuit here. N cells be connected in series in one row. So in one row, I have how many cells here? I have N cells. This is series combination, beta. N cells we have. Like that, how many rows I have? M rows we have, guys. The first row, this is our second row. So like that, I have how many rows here? And mixed grouping is basically viable for identical cells only. Mixed grouping is basically viable for which type of cells, beta? Identical cells only. So you see, now this particular combination is connected to some external load resistance. So this is our first row. This is our second row. In the same manner, it will continue, and this will be your mth row. This is our first cell, ER. This is our second cell, ER. Like that, overall, here you are going to have which cell? Nth cell. So N cells here, N cells here. So in two rows, how many cells we got? N plus N, which is 2N. Like that, in M rows, how many cells we are going to get? So total number of cells will be equal to M into N beta. Now, identical cells I have told, no? So series combination, what will be effective EMF? N into E. Here also N into E. Here also N into E. So in parallel combination, EMF will remain constant, as you all know. So what will be the total EMF beta? It will be given as N into E only. Now, in this cell, what is the effective resistance? NR. Here also NR. Here also NR. So like that, how many resistors I am going to have? M resistors I will have. So what will be the total internal resistance again? If I use, they have not given total internal resistance here. However, you can just write, guys, total number of cells is given, total EMF is given. So in this case, total internal resistance, if we talk about total internal resistance, each row you have how much beta? In each row you have NR. Like that, how many rows are there? M rows, which are parallel again. So total internal resistance will be, so R effective value will be NR by small m. And in general, what is the current? E effective divided by R effective plus capital R. Yes or no? What did we get E effective? Just now we have seen we got NE. What is R effective? NR divided by M plus capital R. So this I will get it as Mn into E divided by N small r plus M capital R. So always remember, we have one theorem called as maximum power transfer theorem. So for maximum power to be transferred, maximum current should flow. When will maximum current flow? Instead of writing this, guys, MR is equal to NR, better you write I will be maximum when the value of effective internal resistance will be equal to the external load resistance. Whenever the value of effective internal resistance is equal to the load resistance, in that case current flowing through the circuit will be maximum, power developed across the circuit will also be maximum. Clear all of you? Yes or no?
Yes, sir.
Cells understood, guys?
Yes, sir.
Series grouping, parallel grouping, as well as mixed grouping. Mixed grouping is simply combination of series grouping and parallel grouping, guys. Same like resistors only. Instead of resistance, here we have cell as well as internal resistance, guys. Then we have Wheatstone bridge, right? As you all know, what is the basic logic of Wheatstone bridge? You all are aware of it, guys. So whenever you have such type of circuit, if you are able to see this type of circuit, guys, you will check whether R1 by R3 is equal to R2 by R4, or you can check R1 by R2 is equal to R3 by R4. So what we can do here in this situation, if R1 by R3 is equal to R2 by R4, or I can also write R1 by R2 if it is equal to R3 by R4, then what is resistance use again? Resistance basically will oppose the flow of current. So what we can say, then no current flows through our resistance, guys. No current flows through which resistance? Our resistance. So if current only is not flowing, will there be any use of resistance? What is the use of resistor? It will oppose the flow of current. If current only is not flowing, will there be any use of that resistor, guys? No. So if R1 by R3 is equal to R2 by R4, or if R1 by R2 is equal to R3 by R4, then we can simply remove this resistor because there will not be any current flowing through it. Then what will happen? This R1 and R2 will be in series combination. So in series, what will I get better? R1 plus R2. In the same manner, this R3 and R4 will also be in series combination, which will be R3 plus R4. Now you see, between R1 and R2, R1 plus R2 is connected between these 2 points. R3 and R4 is also connected between the same points. So R1 plus R2 as well as R3 plus R4. These are going to be in which combination, beta? These will be in parallel combination. So in parallel combination, 1 by R1 plus 1 by R2 will be 1 by R effective. Understood? This is your balanced Wheatstone bridge. If R1 by R2 is equal to R3 by R4, or R1 by R3 is equal to R2 by R4, no current will be flowing through the middle resistor, guys. Current, what is resistor going to do basically? It opposes flow of current. If there is no current only, will there be any use of it? No. So simply we will remove this resistor, then we can take R1, R2 to be. So always know, if they are asking you to find effective resistance, beta, any circuit may be given. If they are asking to find effective resistance, better check in that circuit if there is any Wheatstone bridge possible or not. If there is a Wheatstone bridge possible, then you can directly do the question. Similarly, it will be applicable for capacitance also. We can write C1 by C3 is equal to C2 by C4. So no charge will be flowing through this capacitor. So I can remove this, guys. So these two will be in series, C1, C2 by C1 plus C2. These two also will be in series, C3, C4 divided by C3 plus C4. And they are going to be in again parallel combination. This is your Wheatstone bridge principle, guys. Then we also have a certain instrument called as meter bridge. So meter bridge is basically used to find an unknown resistance, guys. As you can see here, it is used to find an unknown resistance, but it will work on the principle of balanced Wheatstone bridge, guys. It will be working on the principle of balanced Wheatstone bridge. So on one side you will have known resistance, on other side you will have unknown resistance. So if you have certain length of a wire, now resistance is given as rho L by A. So is resistance directly proportional to, if I take resistance is rho L by A. Is resistance directly proportional to length, beta? Yes. So here in the left segment, you have some R resistance, and in the right segment, you have some unknown resistance, guys. In the left part, you have some length. So corresponding to some length, there will be resistance, right? In some right part, you are again going to have some length. So corresponding to this length, you are going to have resistance. Now what they are saying is this jockey will be made to move on the meter wire, guys. AC is a meter wire whose length is 1 meter, right? Or 100 centimeters, you can say. It will be made to move on this particular wire. At one particular point, there will not be any current flowing through the galvanometer. When there is no current flowing through the galvanometer, I can say the meter bridge will be a balanced bridge. So in that case, what I can write? Resistance divided by length in that segment will be equal to, on the other side, resistance divided by length in the other side of the segment. So X value can be written as R into 100 minus L divided by L. Okay, so it is used to find unknown resistance. And when can you do that? You will move the jockey on this particular wire, guys. At one particular location, there will not be any current flowing through the galvanometer. In that position of the jockey, I can say the meter bridge is balanced. And always remember, the location of the null point, location of null point will be independent of, it does not depend on the resistivity or the area of cross section. And because it is used to find an unknown resistance, always remember, resistance is a physical quantity. And whenever we are measuring a physical quantity, there will always be an error associated with it. So while you are finding an unknown resistance, resistance is a physical quantity. While you measure a physical quantity, there will be an error associated with it, guys. Yes or no? Obviously, there will be an error. So I want to reduce the error. I want to minimize the error, right? So error can be minimized by placing the null point in between, or by obtaining the null point nearby midpoint of the wire, guys. Nearby midpoint of the wire. If the jockey is placed near to midpoint of the wire, whatever error is found in the unknown resistance or in the calculation of an unknown resistance, that error can be minimized. Understood, all of you? Meter bridge works on balanced Wheatstone bridge principle. If the reading through galvanometer is 0, then I can say the meter bridge is balanced. So resistance, known resistance divided by the corresponding length should be equal to unknown resistance divided by the corresponding length. Sometimes they will say if the positions of the resistances are reversed, by what distance will null point shift? Again, same thing. You can solve that, guys, again. So if wherever you have more resistance, length will be more there. Suppose here you have 40 ohm, here you have 60 ohm. So this length will be more. If you reverse it, where will null point shift, to the right or to the left? Let us imagine this is 40 ohm, this is 60 ohm. So this length should be more because the corresponding resistance is more. If you reverse it, where will the null point shift? Will it shift to the left or to the right? See, this is 40 ohm, this is 60 ohm. So just imagine this is 40 centimeters, this is 60 centimeters. I am reversing it now. So this became 60, this became 40. So how much will this become? 60. And this side will become 40. So where did it shift? Did it shift to the right side or not, guys? Initially it was at 40 centimeter mark. Now it will move to 60 centimeter mark. So it will shift to the right side. So such type of questions will be asked. What will be the shift in the jockey or null point? Such type of questions will be asked, guys. Clear, all of you? So please do remember this particular case where unknown resistance can be written as known resistance into 100 minus L divided by L. Okay. You have some measuring instruments, guys: ammeter, voltmeter, galvanometer. So basically, if we talk about ammeter, it is a current measuring device. And how it is connected, beta? It is it visible, all of you? Is it visible, everyone?
Yes.
So what is ammeter? It is a current measuring device, guys. How it is connected? It is connected in series. So as you can see, it is correct. It is usually connected before the resistance, guys, because while current passes through the resistance, there may be some losses again. So ammeter may not give correct reading. So that is the reason it will be connected before the resistance again and in series. And if you take ideal ammeter, it will have zero resistance, guys. These 3 points are important in ammeter. And if you want to convert a galvanometer into ammeter, let us say you have some galvanometer, guys. It also has some resistance, let us say some G resistance it has, guys. And let us imagine if only galvanometer is there, some current I is flowing. Right now, I want to convert this galvanometer into ammeter. So what I'll do, guys, in order to convert galvanometer into ammeter, I am going to provide a certain shunt resistance. Shunting is always done in parallel beta. So small resistance I am going to provide. G is the resistance of galvanometer. Here also G is the resistance of galvanometer. Now you see, initially I current was flowing through galvanometer. Now when I convert it into an ammeter, I current will not flow beta. Some Ig current will be flowing through the galvanometer. The rest of the current will flow through the shunt resistance. Now this entire situation will become your ammeter. Now as you can see, galvanometer and shunt resistance, they are connected within two same points. So we can say that they are in parallel. So in parallel, potential difference will remain same or not? What we can write? Ig into capital G can be written as I minus Ig into S. So how much shunt resistance is provided? Direct case you can remember, Ig into capital G divided by I minus Ig. Clear all of you? So in order to convert a galvanometer into ammeter, what I'll do, I will shunt the galvanometer. What is the meaning of shunting? We are providing a very small resistance in parallel. So initially you see I current is flowing through galvanometer. Now how much current is flowing? Only Ig current will flow. Because you are providing very small resistance, guys, almost the entire current flow will be through the shunt resistance only. This entirely will become ammeter now. In the same manner, we have something called as voltmeter. It is a potential difference measuring device, right? It is used to measure potential difference. Ammeter is connected in series, guys. Voltmeter will be connected in parallel. As you can see, across resistor, if I want to find the potential difference, so I will connect a voltmeter in parallel to that particular resistance, guys. An ideal voltmeter should not draw any current. So ideal voltmeter will have infinite resistance. Through ideal ammeter, entire current has to flow. If the ammeter is to be ideal, entire current has to flow. So ideal ammeter will have zero resistance, whereas ideal voltmeter should not draw any current. So for it to not draw any current, its resistance has to be infinite. And how can I convert a galvanometer into voltmeter, guys? So you see, we have a galvanometer, let us take. We have a certain galvanometer. Okay, G is the resistance, and let us say I is the current. So in order to convert a galvanometer into a voltmeter, guys, I am going to provide a large resistance in series. I am going to provide a large resistance in series. Now this will become voltmeter, guys, whose reading, let us say, is V. So if voltage reading is given, what is these two are in series or not, beta? So what is the effective resistance? G plus R. How much current is flowing? I current. So this is the potential difference. So how much is the potential difference between these 2 points? It will be equal to the voltmeter reading. So I can write G plus R value will be V by I. So from here we can write the resistance that has to be connected in series in order to convert a galvanometer into a voltmeter will be V by I minus G. As you can see, V by I minus G or V by Ig minus G also you can take. Clear all of you? For ammeter to get, for galvanometer to get converted into ammeter, shunting. For galvanometer to get converted into voltmeter, adding a large resistance in series. Shunting means adding a small resistance in parallel, right? In order to convert a galvanometer into voltmeter, we are going to add a large resistance in series. Clear? And how much resistance I need to add, beta? It will be V by I minus resistance of the galvanometer, guys. Understood? Now, why do we use another device, potentiometer, instead of voltmeter? Voltmeter will measure potential difference only. And in the same manner, potentiometer is also going to measure potential difference. Both are used to measure potential difference only. But what is the problem with voltmeter is, what is the disadvantage of voltmeter is, while measuring potential difference, it will draw some current from the circuit. So whenever it is drawing some current from the circuit, it will not give correct potential difference value, guys. So that is the reason we are going to replace it with potentiometer. It is a device which is used to measure potential difference, but it does not draw any current from the circuit, guys. So it gives a correct reading of the potential difference. Clear? So we are going to have two circuits, guys. One is a primary circuit, other is a secondary circuit. So primary circuit will be something in this manner, as you can see. You will have a cell, you will have a variable resistance, you will have AB is a potentiometer wire, guys. Now, two very important properties you need to know. This particular potentiometer wire will have high resistivity and low value of alpha, low temperature coefficient. The potentiometer wire, AB is potentiometer wire, guys. This is potentiometer wire. This potentiometer wire should have what, beta? High value of resistivity and less value of alpha. So what does primary circuit contain? It will contain a cell. You may be given a dynamic resistance, or it is also called as rheostat. It may be there, it may not be there. You will have a potentiometer wire. What is the condition of, or what are the properties of potentiometer wire? It should have high resistivity and low value of temperature coefficient, guys. Okay, so if I apply KVL, let us say some I current is flowing. Let us start from here, guys, and we are moving in anti-clockwise sense. Or instead of starting from here, let us start here. Again, you're moving in anti-clockwise sense. Are you moving from negative to positive? Yes. So what I'll write? Plus E. E in primary cell you can write. Are you moving in the direction of current? Yes. Let us say potentiometer wire has resistance R, resistivity rho, L is the length, A is the area of cross section, alpha is the temperature coefficient. Okay. Now, as you can see, while we are moving in the direction of current, are we moving across the resistor or not? So in the direction of current, potential usually decreases. So I'll write minus I capital R. Again, you will be moving in the direction of current only. So I'll write I minus I RH. Again, you will move in the direction of current across the resistor minus IR. You are coming back to the same point. You will write it as 0. So what will I get? I value as beta. It is EMF in primary circuit divided by capital R plus rheostat plus internal resistance. This will be the current flowing. Just like perpendicular axes are independent, X and Y are independent, guys. In the same manner, primary circuit and secondary circuit are independent. What are independent? So primary circuit is independent. You will write KVL equation for primary circuit separately. You will also write the KVL equation for secondary circuit separately, guys. Now, across A and B, what is the potential difference? I current is flowing, resistance is R. So what I can write? Potential difference across AB, I can write it as I into R, which I can write it as I rho L divided by A. So potential difference per unit length will be given as I rho by A, guys. This potential difference per unit length is only called as potential gradient. It is called as what, beta? Potential gradient, and this will be utilized to check the sensitivity of potentiometer. So usually sensitivity should be smaller, guys. So how do we obtain smaller sensitivity? By increasing the length, or by decreasing the potential difference, or by decreasing the current flowing through the potentiometer wire. Okay, so potential gradient is utilized to find out the sensitivity of potentiometer. And how should the sensitivity of potentiometer be? The sensitivity of potentiometer should be smaller. How is this obtained? Either by increasing the length or by decreasing the current. Two ways: increasing the length or by decreasing the current flowing through the potentiometer wire. Clear, all of you? KVL in primary circuit understood? KVL in primary circuit understood, beta?
Yes, sir.
I hope it is understood. Okay. Then what we are going to do is, now this particular potentiometer is used to either find the unknown resistance or the internal resistance, as well as the it is used to compare the EMFs, guys. Okay. So what will happen is, in the below part will be secondary circuit. Secondary circuit is independent of primary circuit again. So let us say first one cell is connected, right? And you got null point somewhere at length L1. So potential difference will be proportional to resistance, can I write? Because V is equal to IR, no? And resistance is proportional to length or not. So what do we use here? What is the principle in potentiometer, guys? It is very simple. Whenever we talk about potential difference, whenever we focus on potential difference, it will be proportional to the balancing length, guys. It will be proportional to what? Balancing length. This is the principle utilized while solving questions of potentiometer. So first what they'll do, they will, in secondary circuit, they'll connect one cell. Now when they are connecting this cell, let us say null point is obtained at L1. So balancing length will be L1, guys. Now, so it means potential difference will be proportional to L1 here. Then when they are connecting another cell E2, then they will say the balancing length, null point is obtained at L2 length. So from here we can say E1 by E2 will be equal to L1 by L2. Directly we can write. Now, this is individual, one cell I am connecting, guys. This is to compare EMF. Whereas now what they will do is they will connect two cells, guys, together. First case is one cell separately. Second case will be two cells together. Now what they are saying, in the secondary circuit, two cells are connected such that they support each other. So whenever they support each other, the effective EMF will be E1 plus E2, guys. This is the situation when one cell is connected. This is first case, guys. One cell is connected. This is second case when two cells are connected. How are they connected? In such a way that they are supporting each other. Supporting each other means you should add the EMFs. In this case, the balancing length is L1. Then they are opposing each other. It means E1 difference E2 will be proportional to L2. So what will I write again, beta? I'll just write E1 plus E2 divided by E1 difference E2 will be equal to L1 by L2. So from this, if I solve this, no, again it is used to compare EMF. So I'll get E1 by E2 as L1 by L2 plus 1 directly, guys, divided by L1 by L2 minus 1. Two cases can be asked, right? One cell connected, LKG problem, guys. Two cells connected, very important again. How are those cells connected? Either they will support each other or they are going to oppose each other. So if they are supporting each other, E1 plus E2 will be effective EMF. If they are opposing each other, E1 difference E2 will be the effective EMF, guys. And overall, when they are supporting, balancing length is L1, they will say. When they are opposing, balancing length is L2, they will say. They'll ask you to find ratio of the EMFs. It will be given as L1 by L2 plus 1 divided by L1 by L2 minus 1. It is also used to find internal resistance of the cell, guys. Right? So how will you find out? Very simple logic. Again, in the secondary circuit, let us say only cell is connected. To this cell, external resistance may be connected, it may not be connected. Again, as I said, this is primary circuit, completely independent of secondary circuit, guys. So if only cell is connected with key open, then will there be any current flowing through the circuit? Open circuit means no current flowing. When no current is flowing, what will be the potential difference across the terminals? EMF, guys. So first case, what is it? Key is open. Key is open means circuit is open. So what is potential difference across these ends? It will be equal to EMF only. So let us say in first case, it is L1. Now what we are doing, key is closed. It means there is some load resistance connected. So as soon as key is closed, in the secondary circuit, some current will start to flow. So what is potential difference across the terminals of the cell when current is drawn from the cell? It is V value. It will be proportional to L2. So from here I can write E divided by V will be equal to L1 by L2. V can be written as E minus IR. It will be equal to L1 by L2. So from this, they will ask you to find R value, guys. And what is E? What is I value that you are going to get? You will get it as E divided by capital R plus small r, or R external plus small r, you can write. This is secondary circuit beta. Secondary circuit will be independent of primary circuit. So from this, you will get internal resistance value as capital R, external resistance, external load resistance into L1 by L2 minus 1. Very important formula again. In order to calculate the internal resistance, very important formula beta. Initially in the secondary circuit, key is open. Key is open means circuit is open. When circuit is open, no current will flow. Now what has happened? Key is closed. When circuit is closed, means current will be flowing. So when no current is flowing, potential difference across the terminals of the cell EMF. When current is starting to flow, potential difference across the terminals will be equal to volt potential V value, terminal voltage, guys. So please remember, the internal resistance value will be given as how much beta? Will be given as external load resistance into L1, balancing length in first case divided by balancing length in second case minus 1. Clear? RC circuit usually questions will not be asked, but basically remember the formulas in this, guys. In RC circuit, we have two cases. We will charge the capacitor and we will discharge the capacitor. So during charging of the capacitor, initially uncharged capacitor will be connected to a resistor with the help of a supply, guys. So in this situation, charge on the capacitor increases following this particular equation. Q naught into 1 minus e power minus t by RC, guys. And this t by, so what is that RC called as? RC will be called as time constant of RC circuit. So whenever charging of capacitor is done with the help of resistor, charge on the capacitor will exponentially increase following this particular equation. And what will happen to current beta? Current will be exponentially decreasing, as you can see. So current value will be exponentially decreasing. RC will be time constant. What is I naught value beta? It is the maximum current flowing, which is given by E by R. And what is Q naught value? It is the maximum charge. It is given as E into C, or V into C also we can write. Okay. Right, we will get it by writing KVL, performing integration. So I'm not going in detail about that. Whenever an uncharged capacitor is connected to a resistor, charging of the capacitor will take place. Charge on the capacitor will increase by following this equation, Q naught into 1 minus e power minus t by tau. Tau is nothing but RC. And current flowing in the circuit will be exponentially decreasing following I naught e power minus t by tau. Clear, all of you? So what is the meaning of time constant? That particular time wherein which 63% of charging is completed, or 63% of current has got reduced, guys. Clear, all of you? Yes or no? So always remember one very important point in RC circuit, guys. Very, very important point. Whenever we take initially, guys, at t is equal to 0, initially if I consider, right, capacitor is uncharged. Yes or no? What is the use of capacitor? It will store charge. Yes or no, guys? Capacitor will store charge. So at t is equal to 0, I am giving charge to the capacitor. So as I am giving charge to the capacitor, it will readily accept. So what will happen? Whenever we are talking about capacitor, how will it behave, beta? It will behave like a closed switch at t is equal to 0, and it will behave as a open switch at t is equal to infinity. Means long time after the switch is closed, or at steady state it is also called as. This is the situation at initial state. Initially you can say this will be the steady state condition. So always remember, if charging of capacitor is being done, initially capacitor will behave as a short circuit or a closed switch, and after a long time, means steady state, capacitor will behave as a open circuit, guys. Now in second case, what we are doing is you are going to take a charged capacitor and connecting it to resistance. So whenever a charged capacitor is taken and being connected to a resistance, charge on it will exponentially decrease, guys. current will also exponentially decrease again. I value will be I naught e power minus t by tau. Here, initially charge is given. There, charge will not be given. There, EMF was given, guys. Resistance was given. Here, charge is given. So the maximum current flowing through the circuit will be given as Q naught divided by RC. Clear, all of you? Please remember, uncharged capacitor is connected to a resistor. It is charging of a capacitor in DC circuit. Charge will exponentially increase, current will exponentially decrease. If charged capacitor is connected to a resistor, then what will happen? The capacitor will discharge. Charge will be exponentially decreasing, current will also exponentially decrease. Clear, all of you? Right, we will get these formulas by performing integration. So I'm not focusing on that as of now, guys. Then last things we have again, Joule's law of heating. So whenever some current is flowing through a resistor, usually it will heat up, guys. If constant current is flowing, then I can write the rate or the heat loss can be considered as I square into R into T. Amount of heat produced will be I square into R into T. For which current? Constant current, guys. In the same manner, if variable current is flowing, right, then I will write heat as integral I square dt. And the limits will be applied till current flows through the resistor. Suppose if current is flowing for 5 seconds, so we'll apply the limits from 0 to 5 seconds. So heat will be produced only when current is flowing through the resistor. If current flow is not there through the resistor, heat will not be produced. So for constant current, directly I'll write I square into R into T will be the heat produced. And if you have variable current, you will make use of integration, guys. We also have something called as power. I'm not going in detail about this, guys, but basically whenever you consider power, so I'll just tell you the formulas again. Power can be written as, if you know the potential difference and current, you can write V into I. If you know current and resistor, you can write I square into R. If you know potential difference and resistance, you can write V square by R. You can use any of these, guys. You can use V into I or I square into R or V square divided by R, right? And always remember, whenever you take any appliance, guys, it will have some specific voltage, some specified voltage, right? Some specified power will be given, guys. Power rating and voltage rating will be there. So from there, if suppose if I say the device is rated as P watts and V volts, so I can calculate the value of resistance, guys. How can I calculate? Specific voltage square divided by specified power. Now always remember, suppose if a device has a rating of 230 volt, it means it can operate till 230. So if the voltage, so I'll just add here PS, I will write specified voltage and specified voltage and specified power, guys. So resistance of the device will be given as specified voltage square and divided by specified power. So if the potential difference across the appliance is more than specified power, guys, that appliance will not function at all. And what will happen? It will get destroyed, guys. In the same manner, if the power across the appliance is also more than its specified power, then in this case, what is going to happen? The appliance does not work. And it may get spoiled, guys. It may get destroyed again. So usually this will be the case where bulb fuses, guys. So when will a bulb fuse? If the potential difference across the bulb is more than its specified voltage rating, or if the power across the bulb is more than its specified power. In such case, the bulb will be fusing, guys. Clear, all of you? Yes or no? Different combinations are there which are not that much essential. Again, you can do these questions at any point of time, guys. And as I said before, just now in I think mixed grouping of cells, I have told you maximum power transfer theorem is there. So for power transfer to be maximum, current has to be maximum. So when will current be maximum, guys? When effective internal resistance will be equal to the external load resistance. Okay, so those points you remember. In the same manner, we have something called as fuse wire. So please remember that fuse wire will have less melting point, because this one point to remember. Fuse wire will have less melting point, and yeah, usually they will ask this. And how will a fuse wire be connected? Fuse wire is always connected in series with the main supply, guys. These 2 points you remember. When will again, what is maximum power transfer theorem? Power transferred across the resistor will be maximum when, if the effective internal resistance will be equal to the load resistance. As simple as that. Okay, so that is the maximum power transfer theorem. For power to be transferred to be maximum, current should be maximum. When will current be more? If external resistance and internal resistances, both the values are equal. Okay, and power value can be written as V into I, or I square into R, or V square divided by R. Clear, all of you? Understood or not? When will a appliance fuse, or when will it get destroyed? If the voltage across that particular bulb or appliance is more than specified voltage. If power is more than specified power, then it will get it will burst, or it will get destroyed, guys. Clear, everyone? Yes or no? This was the review of your current electricity. So we started with the definition of current, how to find current, how to find charge, what would be the expression for current density, right? How is drift speed changing in when you have same current, when you have same potential difference? What is Ohm's law? We have seen color coding of resistors, right? We have discussed what would be temperature dependence of resistivity, variation of resistances. We have seen, right? What is cell? We have seen related to cell. What is EMF? What is internal resistance? What is potential difference? Right? Grouping of cells we have discussed. Wheatstone bridge we have seen. We have also discussed meter bridge, different types of instruments, ammeter, voltmeter, potentiometer. Right? We have also discussed regarding RC circuit, both cases, charging of capacitor and discharging of capacitor, Joule's law of heating, and power developed in the circuit, guys, or in the resistor. Any doubts, everyone? So tomorrow we'll complete the questions of current electricity. I think we are running 2 days slow, guys. Right? I had to complete it on 8th, but I will be completing it on 10th, guys. We are running 2 days slow. So we will anyhow cover it up in some or the other way. We will cover that up, guys. So don't worry about that. So that would be from my end for today. We'll be meeting tomorrow. Any doubts, all of you?
Sir.
Ji, sir.
Sir, in the potentiometer, the EP represents the EMF,
EP represents EMF in primary circuit.
which is already existing.
Primary circuit will be there. Whatever things we are adding, we are going to do it in secondary circuit. You may add one cell, you may add two cells separately, you may connect two cells together, right? You may connect a cell with load resistance. These all will be done in secondary circuit. Primary circuit will always be fixed again.
Sir, and what is balancing length?
Balancing length means wherever the null point is found out, wherever galvanometer shows zero reading.
Okay, sir.
Right. So that's it from my end for today, guys. So we will be doing questions of current electricity tomorrow, and hopefully you will be writing a test tomorrow, guys. Okay. So that's it from my end. Thank you for joining late, guys. For a few days, please get habituated to whatever timing I may call. Okay. We'll meet in tomorrow's session. Till then, take care, everyone. Thank you all. Bye bye, all of you.
Thank you, sir.